gotta do what the fuck I say!
We aren't here to serve any purpose other than bring prosperity and peace.
I want you to go and order that the information be revealed. It is time for everyone to know the truth and why we are on this planet.
In traditional Newtonian and relativistic physics, the universe is treated as a chronological sequence of events. This leads to the inevitable and circular first cause paradox. If everything has a cause, what caused the beginning? Within the quanta physics theory, QPT, this paradox is resolved by identifying two fundamental errors in classical thought: the personification of energy and the reification of time. 1. Time as a measurement, not a dimension. The question, who created God, energy, requires a before. However, as established in this model, time is a man-made mechanical measurement used to track the movement of matter. It is not a physical fabric that exists independently of the grid. In a universe where time is not a physical thing, the concept of a beginning is a human biological projection. The kinetic grid does not exist in time. Rather, time is what we call the observation of the grid's internal vibrations. 2. The perpetual pressure. Gradient. The origin of energy is not a historical event, but a structural necessity. In the 2:1 space-expanse ratio, existence is defined by a constant state of pressure. So, Einstein's mistake, or maybe more accurately, his limit, was assuming that mass energy and mechanical energy are, permanently locked together. He believed that as you add mechanical energy, like speed, it just automatically converts into matter energy, or mass. To reach the stars, we actually stop trying to increase the E and E equals mc squared. Instead, what we do is isolate the matter energy, which is sort of like the taxable energy, and then apply the mechanical energy. That's the pursuit energy. This approach honestly turns the ship into a kind of mechanical bullet traveling through a static void. The cool thing is, you don't need infinite energy to go faster. Just 1 kilowatt of mechanical thrust would keep accelerating the ship at the same rate, whether you're going 10 miles per hour or, wow, even 10 times the speed of light. In the so-called ghost pursuit, the ship follows its path based entirely on pure mechanical input. Since the vacuum doesn't detect the ship, because the matter energy is actually shielded, there's no drag, no time dilation, and yeah, no mass increase. So, thus, adjustment in E equals mc squared over v squared in the quantum physics model actually changes the energy mistake. The lock in space. Even as we refer to mechanical energy and mass energy, also called matter energy, they are, two different types of energy compound. We should also take into consideration the void of space. There's the little g and big G gravity. In a reverse repulsion space field, the indifference to mechanical energy and mass energy, which usually intertwine under Earth's gravity, doesn't really apply in the zero-point energy or dark energy vacuum. The vacuum here, Well, it's an empty void that was already filtered during the cooling process just after the Big Bang, when elusive debris was attracted and eventually formed the planets, stars, and the galaxies. Now, when we review the E=mc² interchange, where, Einstein assumes that the mass of the ship is increasing as the ship accelerates, we should also assume the fact that it's actually the mechanical energy, the propulsion energy, that increases to boost the ship's velocity rate and speed. So, can we assume that the increase of energy mass, as Einstein puts it, is actually what's increasing as the ship accelerates, and not the ship's mass itself? In any case, infinite mass isn't really due to the interchange of matter, or mass, where a solid object is physically manufactured. If that were the case, we couldn't, manufacture the molding of matter with less resistance. Matter mass and energy mass, well, they have different qualities. Reviewing the qualities of E=mc² gives us the assertion that, as acceleration increases, and we get close to light speed, it's actually propulsion energy that balances how heavy the ship feels as it travels. The ship gets heavier due to mechanical mass. This might be true, especially since relativity is under the stress of, planet gravity. But, such an event in space leads us to believe that mechanical speed is really channeled to acceleration and not to weight. Since this weight mass is, the conversion to the mechanical speed, it actually becomes the totality of the ship's mass, weight. And, as we all know it, the only weight of an object is its physical weight mass compiling acceleration mechanical mass, or kinetic mass, to be converted into the weight of acceleration and not at all a physical measurement. It's a moving mass where the weight, or mass, is neutralized even under Earth's gravity. Assuming this is true under relativity theory, it is the mechanical energy that, tears the problem of raising a ship's mass, weight. As such, mechanical energy acts kind of counterintuitive to what our ship might crash into during its journey. It's not that energy and mass are just manifestations of the same thing, but that it's mechanical energy that plays in totality to space travel, where, honestly, there exists no limit to travel.
Faster-than-light transport is achievable when motion is transferred from the spacecraft to a cosmological carrier field, whose dynamics are not bound by local relativistic velocity limits. In this framework, energy does not accelerate mass. Instead, energy enables coupling to a pre-existing cosmological transport mechanism.
The twin paradox is the ultimate bicycle race taken to a cosmic extreme. It's a thought experiment used to show that time dilation isn't just a math trick, it has permanent physical consequences. Imagine two identical twins, Alice and Bob. Alice stays on Earth. Bob hops on a rocket, or a very fast bicycle, and travels to a distant star at nearly the speed of light, then turns around and comes back. According to special relativity, moving clocks run slow, so from Alice's perspective, Bob's clock is actually ticking slower. When Bob returns, Alice is old, and Bob is still young. The paradox, well, it arises from a simple question: who is actually moving? Relativity says there is no fixed spot in the universe. From Bob's point of view on the ship, he is sitting still, and Alice, along with the Earth, is the one racing away from him. Therefore, Bob could argue that Alice's clock should be the one running slow, and she should be the younger one when they reunite. They can't both be younger than each other, so who is right? The tie is broken by the fact that Bob had to accelerate. Alice stayed in one inertial frame. She never changed speed or direction. Bob had to fire his engines to speed up, fire them again to turn around, and fire them a third time to stop at Earth. That turnaround is the key. Because Bob underwent acceleration and changed his path through spacetime, he is the one who switched frames. This makes his experience of time fundamentally different from Alice's. We don't have rockets fast enough to keep humans young yet, but we have proven this with atomic clocks. Back in 1971, physicists actually flew these ultra-precise clocks around the world on commercial jets, and when the planes landed, they compared the clocks that had traveled to the ones that had stayed on the ground. the wild thing? The traveling clocks were just a tiny bit behind. Astronauts have experienced this too. Scott Kelly spent a whole year on the International Space Station while his twin brother Mark stayed on Earth. Since Scott was racing around the planet at about 17,500 miles per hour, he is now technically about 13 milliseconds younger than he would have been if he'd just stayed home. Now just imagine, if you could travel at 99% the speed of light for what felt like 1 year to you, more than 7 years would have passed for everyone back on Earth. So, where would you go first if you knew you were traveling into the future? That's a big yes to the cosmic waiting game. Since you'd be traveling into the future, you are essentially buying a one-way ticket to see how humanity turns out. If you chose a destination like Proxima Centauri, which is the closest star system to us and about 4.2 light-years away, and traveled at 99% the speed of light, so, from your perspective, the trip would feel like it took about 7 months. Honestly, you'd barely have time to finish a long TV series before arriving. But, from Earth's perspective, they would have waited over 4 years for you to get there. And, if you turned around and came back immediately, you would have aged only 14 months. So, everyone on Earth would have aged 8.5 years. If you push the speed even closer to let's say 99.99%, you could spend a few years traveling and return to Earth hundreds or even thousands of years in the future. You'd be, well, a living historical artifact. So, the reality of this so-called race is that, to actually make it happen, we really have to solve what's called the energy problem. I mean, to get something like a bicycle, or, a spaceship, to 99% the speed of light, you need an incredible amount of energy, because as you speed up, you basically become heavier. Your relativistic mass increases, making things way more challenging. Essentially, what's happening is the universe itself kind of starts pushing back against you, making it harder and harder to accelerate the closer you get to the speed of light. Since you'd be jumping years into the future, what's the one thing you'd be most curious to check on when you landed? Would it be the technology, the politics, or maybe just to see if we finally have flying cars? Realistic mass increase has actually been labeled out in future space travel technology based on space expansion theory. The energy constant, E equals mc squared over v squared, is based on the idea that energy is a propulsive energy and doesn't really make a ship heavier. It's just for thrust in the reality of a ship.
The speed of light is the highest measurable speed. Does not mean the fastest a ship can travel to which it is referred with in physics. Space is a vacuum unlike Earth's gravity, which is measurable. Space has no gravity. It is these two quantities the speed of light speed limit is referred by. If the vacuum has no gravity, which slows moving masses when moving through, the speed limit changes. Why? Because no gravity. Relativity also refers the vacuum of space, the vacuum, to be made of the same quality as Earth's filled gravity field. This also is measurable and in the same way. In space, light speed source is conserved, meaning it doesn't stop there. Further acceleration can convey by Newtonian mechanics and dual acceleration theory. The reason for thus is empty vacuum. Silpstream, faster than light speed corridors, become reality at the most deepest depths of empty vacuum. Because no resistance. Gravity acts as resistance to moving objects moving through space. Veli-City changes include resistance gravity fields. In space where resistance is zero, or almost. More energy propulsion can be implied. These are the foundation mechanics on the quantum physics theory that will replace relativity. Rodney Kowecki.
The space expanse velocity is equal to twice light speed, measuring 0 to 14.8 billion years age. The expansion rate in terms of light speed variables, we have to convert the standard Hubble constant h0, which is usually measured in km/s per megaparsec, into a frequency or a percentage of the speed of light per unit of distance. The expansion gradient, h0 in terms of c. The current expansion rate is approximately 70 text s mpc. To see this in terms of light speed, CER approx. $300,000 /baud. At 1 megaparsec, the expansion is 0.023c. At 4,300 megaparsecs, the Hubble radius, the expansion is exactly 1.0c. At the edge of the observable universe, the expansion is approximately 3.2c. In other words, for every 4 billion light-years of distance, you add exactly 1 light speed to the recession velocity, the time variable, 1h0. Another way to look at this is by using the Hubble time. If you treat the expansion rate as a frequency, it tells you how long it takes for the road to stretch by a factor of e, about 271. The expansion rate is roughly 114, 4 billion years. This means that every year, a light year of space stretches by. Settings. Use appropriate media.